Good morning, everyone. Thank you for joining the June 14th Volta call. We've got 3 presentations planned today, and just a reminder for everyone, we do record the session, so please keep that in mind during presentations and discussion, as we will post the recording later to YouTube on the Volta playlist. And with that, we've got 3 agenda items today, or 3 presentations, the first 2 by Sienna and then the third by Northport. So with that, I will go ahead and give presentation rights over to Stefan. All right, so those should be available for you now.
All right, okay, so let me just share my screen. Are you able to see that yet?
Yes.
Okay. All right. So today I'll be discussing, talking about the performance baseline of our current release of Volta, so the Volta 1.3, the last release. This performance baseline testing was done to determine, well, to define the baseline for our future releases, to see how we can, how our software can perform in different situations. So I have defined a number of test scenarios, and all tests have been run on a single physical server on which I have deployed the latest Kubernetes release, which is 1.9.5, and I use the Volta Playground, which I made available a few months ago, to deploy the environment for. So I use this environment to make it quick, to have a quicker deployment in order to run my scenarios more quickly. So here is essentially the layout of the environment. So I have a physical server on which I have 2 CPUs, so I think they're 4 cores each or something like that, with 64 gigs of RAM. And on that, I am running 3 VMs on top of a Ubuntu operating system, along with libvirt and Vagrant. So this is, in a nutshell, what I have deployed. All the container images that were used for the testing were pulled from the Volta Docker Hub repository. So nothing was compiled locally. They were all the pre-built images from Docker Hub, along with the other images, dependent images needed by the Volta environment. So what do I have here as well?
So this is the 1.3 release, is it?
Yes, it's the 1.3 images of the Volta. Yeah, exactly. So this is essentially what all the images that were deployed. So I have all the Volta images and all dependencies. And as you can see, they're all the version 1.3. The only difference here is the main Volta core image was modified a little bit to improve the performance for this to run the scenarios. Again, I don't need to talk about these necessarily.
Stefan, can you specify the changes that was required in the Volta?
Sure. So what I did is I disabled all performance metrics and alarms from being generated to reduce the strain on the system, because when you deploy a simulated OLT a device, then that triggers alarms and metrics. So I wanted to reduce the I/O strain on the system, and I also disabled all the logging on the Volta core. So I only enabled errors from being displayed.
Okay, thanks.
So all tests were executed from the physical server, not from a virtual instance. So this was to limit the strain on the individual VMs. I also eliminated some of the containers being deployed to only concentrate on the Volta containers. And again, I disabled the logging to reduce I/O congestion. And if there's anything else, I'll describe it in the different scenarios. So the first scenario, which was executed on the system, was a scenario to determine the saturation point. The saturation point meaning how many devices can be created on the system before it starts misbehaving, before it starts failing, having less memory available or something. So the first test was executed using etcd as the KV store, and this etcd KV store was run without any volume attached. So it's only using the internal storage. So for this test, again, I disabled the logging, I disabled alarms and performance metrics, and I did some adjustments on the etcd configuration. So this is the deployed containers before I run the tests. So you see we have a cluster of etcd instances. I have Fluentd, Kafka, PCLI, the core. So the ones that I removed in there was, I believe it's the netconf, OF agent, and I think that's it. Yeah. So after I describe all this, I have a number of diagrams that show the overall performance during the test. So while we ran that test, we were able to achieve a saturation point of 2,338 devices. So this is the point at which containers started to die or be respawned, and it became unstable.
Is a device an OLT or OLT and ONU? Or
well, it's a simulated OLT, so that means there would be the OLT plus the 3 or 4 ONUs attached to it as well.
I see. And
so
then
the number here is only for the OLTs. So okay. if you include the total amount of devices, that would mean this times 5. So it's 1 OLT and 4 ONUs.
Okay, and the creation of the OLTs was done by a script that I just created.
Yes, I have a script that. Okay. Yeah, I have a script that just issues a curl command to create the device.
Okay.
And that number represent. Yeah, sorry.
Go ahead.
That number also represents the number of logical devices in the core.
Any more questions? No. Okay. So this is the overall progress of device creation for that test scenario. As you can see, it was pretty constant all the way through. And then around what 8:20 or something like that, then we started seeing a little plateau where the system was starting to maybe it was running some processes in the background, so it stopped responding to requests, to creation requests, and then picked up again until it started until it stopped allowing any requests from going through.
So how many Volta instances are on this test? Is it 3 or?
Yes, so there's 3 vCores. So as you can see in my list of containers here, I have 3 cores. I have the 3 etcds. So it's a 3-node deployment. So
go ahead. The devices are actually being distributed to, across all the 3.
Yeah, so it's a round robin type operation. So it's going to create one on the first instance, and the next one, and then so on. So you can see those are running on separate containers, K8, S1, 2, and 3. So the diagram, so I have split the diagrams based on each VM. So here we display the CPU usage on the first VM instance. You can see that up to the 820, it was constant, and then which matches the little plateau area of this diagram. And then it continued on until it stopped accepting any requests. So then at the 2026 or something like that, it started failing, and instances started being respawned or died just completely.
Do you know what happened at 8:20?
At 8:20, I believe there was some sort of compaction process on the etcd side. So I think it just, okay. Yeah. So there was something that was preventing anything from being written for a little bit.
Stefan,
yes, go ahead.
When you say device creation, does it mean like ONU activation, or is it what does device creation mean?
So the script, what it does, it issues a curl to actually provision a device, and then I enable it as well.
So provision an OLT device, you mean?
I provision a simulated OLT, and I enable it as well.
Okay, so nothing. This is not about ONUs. It's just provisioning an OLT.
No, there's OLTs and ONUs because it's a simulated OLT, so it provisions the OLT plus the 4 ONUs.
Okay, but obviously, yeah. So there's nothing about ONCI messaging happening.
There's no.
Right. Okay.
No, it's the simulated OLT is part of the core, so it just do some simulation. So it doesn't do much. So it's really everything is happening within the core. There's no data that's going out of the core when we use simulated OLTs.
Yeah. So so this definitely can be extrapolated for the realistic scenario, but it is just not very close to the realistic scenario of actual OLT and basically ONUs being activated.
Well, from a core memory utilization and CPU utilization perspective, it's very close.
Correct. Okay. Yeah.
Right. So what we were trying to do is assess how the core would perform under the loaded conditions, and I think this comes very close.
Right.
And even closer when, say, when the adapters are separated from the core, then it's 100% the same as you would see if you had or didn't have OLTs, other than the duration, because transactions might take longer, right? If you're going to create a real device as opposed to a simulated device.
I agree. Yeah. This comes definitely closer when we post containerization.
Yep.
Okay.
Although
Thanks.
the I guess the frame decomposer load, as we incrementally add more ONUs, I guess would be missing from this, right? Because we're not receiving the open flow messages.
Yeah.
You think is that significant, or?
I don't think so. I need to give that some thought. There's not a lot of open flow messages.
Right, but for every.
Sorry. Yeah. So Sean, yeah, I also think there is something that needs to be considered, because as long as you are dealing with a logical device which does not have too many children, it would be different from dealing with a logical device which has a lot of children, right? Because in most of the cases we would be running through those loops. So having more ONUs, I think, will change the situation up to quite an extent.
Okay. So any more comments here? No? Okay. So I'll move on to so I have a number of diagrams for the different VMs. So I started with the CPU usage diagrams. So this would be on the second instance of the VM. So it's similar to the other ones. So you won't see any major differences. So in some cases, you'll see the VMs have respawn. As you can see, the Volta etcd retry 1 is an instance that got respawned or died.
I guess around that 820 period again. So if the compression is occurring in etcd, does that not show up as CPU utilization, or is that somewhere else that's happening, or?
You know what? I'd have to check my logs again. I don't remember what happened exactly here. But
in terms of the vCore, since this is twisted Python, the library that we use to access a database, it's a synchronous call to a database. It's not an async, so it will block if it's get held by the etcd in this case. So I believe what happened at this time, because there's something is happening on the etcd is not responding. So we're kind of waiting to get a response. At that point, twisted Python being a single thread model, it's stuck. It's waiting because the library that we're using now is not an async library.
Right.
It's a synchronous.
But if it's doing work, compressing the database or whatever, I mean, wouldn't that show up as CPU utilization as well, or is it just basically not? It's basically not doing anything within that period of time for some reason.
Yeah. I'm referring more to the vCore CPU utilization. That's why you see it like you go down quite a bit.
The yellow
one.
Right, but there's no commensurate rise on any other CPU core, right?
Mm-hmm.
Well, you know what? So it depends. If it's all I/O and very little work, then you won't see a big spike. There is a little bit of a blip in CPU for etcd. I'm looking at the right color. Yeah, I am. So etcd has a blip right at the start of that drop, and then and if it's I/O bound, right? It's trying to write keys or do a lot of disk operations. You're not going to see a lot of CPU. You're going to see a lot of wait states. So if you do a PS on it, you'd see a lot of waits instead of actually a high CPU. So the load average would probably go up, and that's something that we weren't measuring. So it's hard to say.
Oh, okay. All right. So I guess I won't bring that up again. Sorry, go ahead.
Okay. All right. So again, this is the third instance for CPU usage. Around 2020 is pretty much the same, a bit different. Now we fall into the memory usage. You see the orange one would be the etcd, so it's pretty busy throughout the execution of the test. The green one being vCore. Yeah, so I don't know what else to mention here, except that memory depletion was pretty gradual for vCore. So this is the second instance of second's VM instance. Yellow being vCore, and the third one. So, any more questions for the first scenario? No? Okay. So scenario B is a similar scenario. It's similar to scenario A, but in this case, we ran it against etcd along with a attached persistent volume. So the persistent volume is managed by GlusterFS, so a cluster of GlusterFS containers in this case. And I'm executing the same scenario, so creation of simulated OLTs and enabling them for each instances. For this one, so I did disable logging, alarms, I optimized the cluster, and I also deployed the GlusterFS cluster to allow me to deploy a allow me to add a persistent volume. So the persistent volume allocated to this was 50 gig per instances. So same number of containers were deployed. So this is this one gives you an idea of the memory usage at the end of the test case on the etcd side. So that's one instance of etcd. So I didn't print out all instances. So again, so the creation of devices was pretty constant. We reached a saturation in this case at 1820 devices. So the diagram, similar to the first one for device creation, there's a plateau being reached at some point, and then it goes on for a little bit and dies. So for CPU usage in this case, GlusterFS is pretty busy the whole time. Sort of adding the persistent volume slows down a bit of the creation process, since there's more I/O required. And
sorry, could you just go back to the previous slide for a second, just on the number of devices? Yeah. So yeah, the one with the graph. Yeah, that's it. So I guess if we say that there's say a 32-way split per PON port and the 16 PON ports per OLT. So that would be about 500 devices, I guess, if we just max out the numbers, right? So does that mean there's essentially three, let's say that would represent 3 edge core OLTs with 32-way split on each PON port? Is that what that's saying? So this is 1,800 devices.
Well, 1,800. So again, 1,800 devices is 1,800 OLTs. So then you times 5 for that. So 1,820 times 5 is a total.
9,100. 9,100.
Okay, divide that by 500 gives you the number of physical OLTs that we would expect to be able to support in this scenario, I guess.
Why divide by 500? I'm not getting that.
So if there's 32 ONUs per PON port and the 16 PON ports per OLT, then that gives you 500 devices. Well, yeah, about.
Okay.
So then if we divide, 1,900 by 5, that gives you 4 OLTs, I guess, about.
Let's see. What was that, Stefan? 1820?
1,820 OLTs, yeah.
Okay, so that's 9,100. So divided by 5 gives 500. Sorry, so it gives you 18.
Okay. Yes. Yeah. All right.
And remember, this is a small memory footprint, right? That we're using here. They were all VMs. They weren't big servers.
Yeah, so VMs with 6 gigs each. So.
Yeah. So very few people will run 6 gig VMs when they're running Volta. If you want to handle a lot of devices, you have to up the memory and the number of cores.
Okay, and the number of devices is bound by the memory footprint, or not the CPU.
Yeah, it is. Well, mostly, right? If you look at memory utilization, you see it creeping up until things start to fail. So,
right. Okay.
And if you add more memory, I did this same test last year without actually capturing any of the results on the older vCore, and if I increase the memory, I had 12 gig VMs, so I was able to create almost double the number of devices that Stefan is creating here, and if I doubled the memory, I almost doubled the number of devices that I could create.
Okay. Sounds good.
All right.
Thanks.
So, going back to the CPU usage, in this case, we started seeing degradation at 1806, and so that means some instances, some containers will respawn, and it picked up again the creation after that. And so you see that there's a big gap between a certain period. So what else can I talk about here? I don't want to use up all the time here, so I'll probably speed up through the different diagrams, unless you have questions.
Sorry, this was 5 gig of memory, was it? Or did I
6 gig. 6 gig was allocated for each VM. Yeah, 2 CPUs for each.
Okay.
I have. I'll provide the document afterwards so that everyone can.
Okay. All right. Great. Thanks.
Refer to it. So this is the memory usage. In this case, the green would be the internal etcd. So that's the Kubernetes etcd. Volta blue. So in this case, the Volta etcd died at one point. You got respawn. this one got more busy than the others. Maybe not. Okay, so that's about it. So unless you have any more questions on this, I'll move on to the next scenarios because I have 8 of them to go through. So scenario C is the same scenarios as A and B. Is instead of using etcd, I use console in this case. So console has a volume attached to it. So like our original deployment of Volta, we were using that that format. Again, I created devices and enabled them. In this case, I disabled the logging and alarms and performance metrics. As you can see, the limited number of containers were deployed. So for console, it was pretty constant, like the other two guys, but we did notice more gaps as the scenario went through, due mostly caused by the DB snapshots that console was doing every so often. And the total number of devices created was 1854, but we started to see more degradation at an earlier stage, so at 1641 in this case. So on the diagram, you can see there's more gaps throughout the creation process as DB snapshots are being created. The console execution, the scenario, there were more instances that started failing at an earlier stage, but it managed to recover during the execution of the test. So that's why I said that there was some degradation at this 1641, sorry, at 1452, so 1641 devices created, and it picked up again until it stopped responding. So here it's pretty obvious that something happened here. The colors have changed at 1430 or something like that. So in this case, it was on the second VM instance. Degradation was seen after creating 1342 devices. So there was more respawning happening here than on the first VM. And then this one happened a bit later. Here we see the memory usage. So I guess we could compare with etcd, but I would have to go back to the other diagrams. So in the case of console, it did start to degrade, but it recovered. As for etcd, it kept going until it stopped responding completely. So any more questions on the scenario C? So scenario D, we changed the scenario here. Our objective is to achieve a loaded state. So loaded state meaning we're trying to have 80% of the saturation point that we achieved in the previous scenarios. So in this case, we executed this test against the etcd with a persistent volume attached to it. And again, we disabled a few things. and optimized, and installed a Gluster FS cluster. So no differences here in the terms of containers at CD and along with the other containers. Okay, so the scenario will create a number of devices until it reaches that 80% mark, and what we do afterwards is we try to we terminate a vCore to see how it will behave. So in this case, as soon as I terminated a vCore, I started losing my etcd cluster gradually. So the etcd cluster, each instance started dying one by one, essentially. Probably because the vCore is bombarding the etcd with requests to pull out the information. And also because there's a lack of resources. But there is some known issue with the etcd component itself. So the way we deployed the etcd cluster was through the etcd operator, and the etcd operator manages the whole detection of liveness and health of the etcd instances. So the operator takes care of killing and restarting etcd when it detects issues. But I think there are some problems with the actual component. I have no diagrams for this test case. The next one is recovery. We tried to lower down the loaded state for that etcd instance, etcd with PV. So we lowered it to 60%. So we executed the same test case as scenario D. Again, we did all of this configuration, same container deployed. In this case, we created, we reached that 60% mark, and again, we killed that vCore instance. As soon as the vCore instance was terminated, one of the etcds started showing a ready status of 0-1. So it's when that shows 0-1, it means that there's the liveness is starting to is not responding to the operator or something, and it's busy with something. So in this case, it's busy getting giving the information to the vCore, but it eventually recovers after a couple minutes. The problem with this, with the etcd case though, when there's that recovery period, as you will see in the diagram after this, in the diagram here, you see I'm not seeing any responses back from the API. So in this test case, what I'm doing also is I'm pulling the device information. I'm doing essentially a get list of devices every second or so, and I'm trying to get that information and then kill my vCore and then wait until the recovery is complete and see how long it took to recover. So in this case, it was not responding for the whole time of the recovery. So the next test is the same test as the recovery of etcd, but in this case with console. We tried the 80% loaded state. I disable logging, alarms, PMs, same containers. So the system was stable during the creation, like we noticed in the saturation test case. And once we reached the saturation, the loaded state of 80%, the vCore was terminated, and I was issuing my get list of devices during that period, and the API was still responding the whole time, although it was only returning the 2/3 of the devices, which is expected in this design. And it fully recovered within a similar period as the other one, as the etcd test case. But the advantage here is it was still responding to my API calls. So there was just a little, approximately 10, 15 seconds gap here. Okay, now we go into a different type of scenario. We ran scenarios to calculate the transaction time when we have a system at 80% loaded state. So what I did is I calculated transaction time from an empty state all the way to the loaded state. And then we see how the response time, the transaction period, is impacted throughout the scenario. So in this case, I had to disable a few things, and I also added some code to monitor to include some logs for the average transaction time to put information into the KV store. So it was pretty stable throughout the execution. And we can see, so that this is the etcd case. It had a 15 to a 17 millisecond transaction time at the beginning, and towards the end it was 16 and 18, which is not a major increase. Scenario H is the same test case, so we calculate against a console KV store. Again, it was pretty stable. In the case of KV store, all instances were at 10 millisecond transaction time at the beginning, and all of them reached a 13 millisecond transaction time towards the end. So my general observations while executing these test cases is we noticed that etcd has issues. It's not able to recover well when in a loaded state, and if you have a lot of information being pulled from etcd starts dying, so all instances will die one after the other, and the etcd operator is not able to restart the cluster, so you lose your cluster completely. So this is not good. So it would need a manual intervention in this case. So I raised the issue with the etcd operator project. I haven't heard back from them yet, so it was well documented. So if they need to reproduce it, they can. So I'm still waiting for a response. The other thing is we saw that console is behaving quite well under stress. There's some instances containers that die, but overall it did behave pretty well. So I would say that it's more reliable than the etcd cluster so far. And one thing we need to investigate is maybe separate the master nodes from the worker nodes to see if that would behave better in a deployment. So we still need to test that. I haven't had the chance to do that yet. And the rest of it is the installation details. So I don't necessarily need to go through that unless anybody's interested. But that will be provided in the documentation that I will forward to you later on. Any questions?
So for Volta 2.0, are we saying that console would be the database to use versus etcd, or is that too much of a statement?
It will depend on what we get back from the etcd folks. If it's just a question of maybe some configuration thing that we missed out, or is it there's a new load that we should be using, then yeah, we may need to run some of the tests and with etcd and figure out. But if we don't get anything from them, then I think we'll have to consider console.
Yes. Any more questions? Comments?
Yeah, it's a great presentation. A lot of great information there. Thanks.
Okay, perfect. So I guess we can move on to the next agenda item.
And Ken, should I make you presenter now? Ken, are you still there?
Oh, sorry, I was on mute. Yes.
Oh, okay.
Sorry.
Are you ready for me to make you presenter?
Yeah.
Okay,
Yeah.
and I just want to do a quick time check. So I know we've allocated about an hour for these first two presentations. Are we going to be time constrained here, since we have another presentation lined up that's going to take about 30 minutes?
I think it depends on the how many questions we get.
Okay.
Yeah.
So we may need to reevaluate as we go along and see if we need to defer some questions or continue maybe on Tuesday. We'll see how it goes.
Yeah.
Okay, thanks.
Actually, it's not showing the right one. Can you see my screen?
Yes, we can. Thank you.
Okay. So this one is really the update on where we are currently with Volta 2.0 in terms of the items that we're FONSI doing. And also there is, let me go to the agenda maybe, give you a better idea. So it's on the agenda item, like we'll be discussing about the current state, where we are at 2.0, where we are at containerizing the adapters. We'll also talk about briefly about some of the 2.0 items that will post 2.0 items. But first, I want to start with some general observations because I've been writing some code and I'm seeing that the amount of changes that will be required. Let me go to that slide. So I'm saying that we will need a lot of changes in the core, and there will be quite some change in the adapters. Even if I try to encapsulate the changes to the minimum possible, but still there will be a lot of changes required in the core. And eventually what will happen, because everything is written in implicit Python, we will hit some supportability issues later on, and some performance and stability issues. And most of it is because of the set of libraries that we are limited to when we use Twisted Python. For example, at this time, there's only one Twisted library for Kafka. That's it. There's no other choices. That's the one that we can use to talk to etcd or console. I think there's also one library that we can use for Twisted there. So there's not a lot of options. And Golang is a language that provide long-term supportability. We have a better concurrent support and provide better performance in the long term. And we know that in 2.0, post 2.0 will be migrating to Golang. So all the efforts that we're going to put in 2.0 currently in Twisted Python would be pretty much wasted. So my concern is like, why are we going to spend so much effort in Twisted Python, knowing pretty well that we'll migrate to Golang and we'll waste those efforts? So my question really to the community is, do we want to migrate to Golang right away? And maybe it will be short-term loss, but long-term gain? Or do we want to make all those efforts now in Twisted and then scrap that out of the 2.0 and then move to Golang? And that's a question that I asked to the community at last. If anybody had any comments or anything that they want to talk about.
Can you call Python from Golang?
We could. The only thing is call Python from Golang.
Yeah, can you link them together? Can you, in other words,
that's when you would go probably like an RPC mechanism, like when we split apart the adapters to containers themselves, it'll go over gRPC. One of the points of microservices is allows the developer to pick the language that best suits the needs of the microservice. And then we're using, again, an RPC mechanism between the containers. So an adapter could be written in Python, and it could communicate via the core written in a non-Python language over gRPC.
Yeah, yeah. Or Kafka, as we're planning. Yes. So you know, my view is we should bite the bullet, because it's I mean, just the wasted effort alone would probably justify it. But that means that we need to. How many extra sprints do we need, Ken? Was it 2 or 3?
I think if we want to do it the proper way, there's certain things that need to be revisited. For example, like currently there's no clear demarcation between the core and the adapters, so we need to make a clear demarcation. For example, there is a lot of device management, for example, that is being done in adapters, so that has to be moved into the core. So there will be some design work that will be required first. So I think maybe 3 sprints. We should be additional sprint. We should be able to do that. But I don't know how much work will be required on the adapters though.
Based on what Dave said, maybe keep the adapters for now on the Python.
Yeah, I know, but if Ken's going to move adapter functionality into the core, or vice versa, then all the adapters need to be changed, right? To compensate. They can stay in Python, but the reciprocal changes would need to be made.
Exactly, and also there's a set of libraries that will be used by both sets. So it's better that to have a common language that they can use the libraries easier, rather than having like a library just for Twisted, one library just for Golang.
Yeah, I think from a scalability perspective, I think moving to Golang would be very beneficial, right? I mean, it's just a you know, when do you need to do it? The earlier the better, from my perspective too.
Is it also resiliency is better because of the concurrency and all that?
Well, I mean, one of the things like the OpenOMCI is being written in Twisted Python and it's got a long ways to go still, just for functionality. So switching to Go language might as well. I mean, that's a significant hit because the OpenOMCI runs within the ONU adapter.
So, but as long so if you could keep your adapters in Golang, and not in Golang, sorry, in Python, then you wouldn't take a hit at all.
Yes, that's what I was saying.
So,
you know.
Yeah. So one of the options is, you know, we said we're going to use Kafka, right, as the adapter communication mechanism. Theoretically, you could retain the adapters in Python, but you wouldn't be able to benefit from the Golang libraries that have been written. So, you know, when they do get converted, and so here's another question, right? If the performance is going to be better in Golang than Twisted Python, and you've got a ways to go to finish the OpenOMCI work, wouldn't it make sense to switch before you finished it all, and rather than go back and redo it all again in a different language, or does it not make sense? Let's say you had three additional sprints because that's what was required to, say, make the core changes.
Before Chip answers that, let me ask a quick question. Do we know that performance is going to be better with Golang? I mean, is that a known fact?
Golang is 30 to 100 times faster than Python.
But the thing is also you got to consider is, do you need that performance? What adapters do, depending on, of course, as they come up, there will be points where they do need a little bit of performance. But overall, you know, if adapter is mostly just sitting there waiting for events to happen and the data plane is passing, do you need that performance? You know, it's sort of like you actually need to test and see where there are issues. And of course, in the core, you know, the device manager and all those pieces, they have to manage many things, but
yeah,
do you need that in an adapter? And I don't think you do right now. We haven't proven that.
So Ken, what libraries would the adapters just not be able to use if they retain their Golang implementation and just switch to communicating through Kafka?
Retain their Python implementation.
Sorry, yes, their Python implementation. I'm just partial to Golang, so I'm just going to keep saying that. But yeah.
Well, any library that we have, like that will be developing for Go, for example, to talk to the KV store, libraries to talk to the Kafka, those libraries they will have to be written in Twisted. So currently there are some of it, but it's not all there. But if we go to Golang, then in the core, those libraries will be Golang, and then
and that's so I think that's fine. So the adapters like Kafka and KV store are the two major ones, I think.
Mm-hmm.
We're already communicating with Kafka in Golang. Sorry, in Twisted. Let me get off this Golang. Right. So in Twisted, we're communicating with Kafka already. The core does that. So we're using a Twisted library, right, to do that, one that's out there and open source. For the KV store, if we want to abstract the KV store, well, that's, you know, we can do that in Golang, which will let us swap in, you know, etcd or console or Cassandra or whatever we want in the background as the back end, which is probably the right thing to do. And the adapters just continue to adapt to whatever KV store is there, or one of the adapters writes a library that everybody else uses. I mean, that's not a stretch, right? Really, because containers should really be written in any language you want to write them in, like Docker containers. So if the adapter developer wants to develop their adapter in Twisted, as long as they can communicate with the required databases and and message buses, they can write it in Erlang for all I care, right? It doesn't matter.
How about the IDE?
Report someone writing something in Erlang.
How about the IDE support, David? Is it more comfortable to basically, switch the IDE? What's the constraint on the people who are used to different IDE?
So there's PyCharm, which is a Python IDE, for example. That's a commercial IDE that's available. They also have that same company has one called Golang, which is for Go, right? So your IDE would remain, the look and feel would remain the same. It'd just be a different language. So it depends what you're using as your IDE, right? That's a hard one for me to answer, other than to say there are IDEs out there for Go.
But again, I think the point really is here. Everybody should, as Sergio said, right? A component should be able to choose the language that's best suited for its needs. For concurrency, I would argue Python is not best suited for concurrency. Right? It's just twisted like that. But at the same point, microservices are designed, or one of the points of microservices is to allow incremental migration of components from one language to another if the developer chooses, right? So I think we're, from what we're trying to accomplish, this should be okay. It does mean that the adapters or those components which choose to stay in Python, twisted Python, may have to do some extra work around the library or access to Kafka and the KV store, because
David, so that's a concern I have is, let's say we bite the bullet and the core is rewritten in Go in 2.0. So does it mean that the Python support, some of the Python support for the adapters would be missing? And if I wanted to retain an adapter in Python, I would have to go and write some libraries, the support libraries for Kafka or KV store. Is
right.
That what it?
I'm going to give you a partial answer.
So can I go first, David? Because
absolutely, because
the Kafka okay, that's not why so the Kafka piece has to be done regardless, because that's part of separating the adapter from the core, right? So putting them in their own containers, there's some work required, and some of that work involves communicating with Kafka and communicating independently with the KV backend store. So that work needs to be done regardless of whether we migrate the core to Golang or not. I think what Ken was saying is that if the adapters go to Golang, then they could benefit from the work we're going to be doing in the core for the Kafka communication and the backend, and if not, then those libraries still need to be written for Twisted, right? That was, I think, his point. So David, sorry, go ahead. I didn't.
No, you pretty much covered it. So I think it's just that library, that connectivity to KV store and Kafka that has to be written for Python support.
Yeah. Just one thing to note, it's the Kafka library for Twisted. When we use, I tried and I don't have like a performance numbers, but I can clearly see that overall it's 2 times or 3 times slower than a Golang library. When I publish information in Kafka, it's slower. So that there would be some impact when we talk later on about IGMP messaging, like by double or triple the latencies that I see on Go.
Right, but it would still be overall faster if the core was in Go and even the adapter was, if it stayed in Python, than keeping the core in Python and the adapter in Python.
Yes.
Yeah, for sure.
You get an improvement. Yeah.
Another question I have is for the OpenOMCI. If the OpenOMCI work is done in Twisted, does it mean that all adapters needs to remain in Twisted?
For ONU adapters, that was the original target, and I'm thinking that you can't really separate the open OMCI from outside the ONU adapter. You know, it'd be great if it could run in its own container, but just the specialization, if we'd have that some adapters may need in OMCI, maybe we can find a way to do that, to containerize it, but I don't think it'll be that easy right now. And it's definitely not something on schedule for a 2.0.
I mean, at some point, I think we'd want to be able to look at the OMCI work, move it into a compiled language, because then it could be leveraged within scripting languages, interpreted languages like Python, but also leveraged within compiled languages. For instance, it was like a C library, right? You can use C libraries from Go, you can use C libraries from Python. So there might be some benefit of thinking about that for at least the future.
Yeah, I think that's a good point.
So I'm just doing a time check here because I know we have one more presentation we're supposed to get to today. I have a feeling we need a lot more discussion on the presentation from Ken. So I'm trying to figure out what to do with remaining time today. Go ahead.
I was going to say, let's go to the other presentation and schedule another hour at some point to discuss this whole Golang thing, because I think it's critically important that we make that decision and we talk about it and we understand what the implications are if we don't do it right away. And of course, you know, the schedule hit. I mean, this is open source, so the schedule hit should not be a big deal, but it seems to be. So I want to have that discussion.
Ken's presentation is more than just the Golang issue, too.
Yeah, it is.
Right.
That's correct.
So I want to make sure, you know, Ken has some other good content to share with the community about stuff that they're working on. I don't want to lose that.
Yeah, well, no, we
won't. So do you think, so we'll switch over to the North Porch presentation in just a moment. So hang on just a minute more. And then do we want to use Tuesday's Scrum call and dedicate that hour to the discussion, or wait until Thursday next week?
I think
Tuesday.
Fine. Tuesday's fine, and in fact, what I think we should do is go through the rest of the content first, and then get back to the Golang discussion. So that way, if it goes long, we will at least have gotten through the rest of Ken's presentation before we come back to this.
Okay, so let's do that then. So Ken and Sergio, thank you for your understanding here, and we'll dedicate Tuesday's call for this topic, and then if it's okay, I'll switch over to the North Forge presentation now. Is that agreeable with everyone?
It is with me.
Great.
Sure.
Thank you. And Oleg, should I give you presentation rights, or who should I hand them off to at this point?
Yeah, that's me. Can you hear me, guys?
Yes, I can.
Yep.
I will make you the presenter now.
Okay, not a problem at all. So yes. So I will share my screen. Can you see it?
Yes.
Okay. So okay, so I'm Oli from NoseForge. I hope I will do my best to make this presentation as brief and as short as possible. So first of all, what's the purpose of this presentation? The purpose is that we have started the activity for automated testing, as you pretty much know. And in order to start that activity, we thought that it's maybe better for us to present the list of requirements and maybe a couple of words about the high-level design, in order to make it sure that we all align under the same with the same requirements, because we don't want to find ourselves after some time of development that the requirements that as we understood them wrongly, and so on. Is it clear?
Yeah.
Yes, is it clear? Sorry. Can you
For me,
hear
it is,
me?
yes.
I don't hear feedback from you, so that's why. Okay.
Yes, I think it's clear. Oleg.
Okay, sure. Okay, so first of all, just two slides coming from the North4J's proposal to the community. So here we see a general description of the approach of the automated integration testing. We can see here the system that we're going to test. The system composed of Volta with a Ponzi multi-adapter, communicating with Ponzi, and there is an SDN controller on top of that with the relevant applications. And all the testing environment should be finally triggered by code commit through the cord get it with the hook that triggers the Jenkins job, which runs the relevant test on top of this system. And here is the list of 6 tests proposed by North4J to the community. So the current status is that we here in North4J, we pretty much looks like we finished the learning curve of what's going on in Cord and Volta. We prepared the requirements and HLD and high-level design that I'm going to present now, and we finished our internal POC running Jenkins job with the first OLT provisioning test case in our North4J's environment. So we are working right now in trying and port this POC to the Cord Jenkins. So when it's done, we will be happy to present the demo of the first test case for you. So this is our status. And right now, what I would like to do, I would like to switch to the requirements, and I would like to go requirement by requirement in order to see that we all aligned with the same kind of shared knowledge. So here we can see the wiki page that consists of the requirements and HLD. This wiki page we're gonna enrich by more details during the project, the details about the design and all the information about the tests. So let's go one by one through the requirements. So the first requirement says that the automated, and by the way, guys, feel free to interrupt me anytime you want.
Can I ask a question just quickly? Have you looked at the Cord tester that's already in the repository?
Yes, of course, I looked on the Cord test, and yes, and I'm communicating with Kartik about that.
Okay, perfect. That's fine. That's all I wanted to know. Thanks.
But I will more than that. Hopefully, I will reuse some code directly from there, or kind of copy paste or whatever. So yeah.
Okay, great. Thanks.
Okay, yeah, requirements. So the first one is the automated testing system should include the following components, exactly what we have in the slides: Volta, ONOS, Ponzi, Volta, and SDN controller and the relevant applications. The automated testing system should be invoked from Cord Jenkins. That means that it should be aligned with the Cord Jenkins style of JJB YAML jobs configuration. The automated testing system should be triggered either manually or automatically by Jenkins scheduler or triggered by get commit or whatever. So 2 options are relevant, manually and automatically. The automated testing system should implement the following test cases, and here we can see the same 6 test cases that were proposed in North4J's proposal. The automated testing system should supply, I'm on the 5th requirement. The automated testing system should supply the ability to choose the origin, the source of the running components. Components, I mean source code, container, images. And this requirement has 2 kind of sub-requirements. The first short-term requirement says that the parameters form, meaning the Jenkins job parameter, should allow the definition of the location of the images for the running components. Here, I mean that when we start developing the tests, we assume that the system was already deployed somewhere. And in a Jenkins job, it should be a parameter pointing where the system is deployed. This is for the short-term requirement. And for the long-term requirement, we mean here that it should be the chain of jobs, one job having several stages that actually starts from the commit, goes to the Git pool of the whole source code, then building the source code, deploying it, and afterwards running the tests. So in this case, in the long-term requirement, the Jenkins job input parameter actually includes the repository and the branch. Is it clear? I hope so. Okay, so I'm going to the next requirement, requirement number 6. The automated testing system should be part of Volta Core CI, continuous integration system. The Volta testing system should supply, of course, like every system, success and failure, or green and red status according to the Jenkins terminology. The requirement number 8, the automated testing system should attach the logs from the tests, all possible logs to the Jenkins job as an artifact for the further investigation. The automated testing system source code should be managed by Volta Core version control, get it in our case. Requirement number 10, the automated testing system should be aligned with Volta Core coding guidelines, of course. The automated testing system should use the pre-configured target machine or cluster if we're using Kubernetes, the machine running Ubuntu 16.04, Kubernetes and Helm installed. And the last requirement says that all components of the automated testing system should be deployed using Helm on top of Kubernetes. That's pretty much all the list of the requirements that we kind of thought about. So if you think that something is wrong, something is missing and incorrect, so yeah, just your feedback is very, very important for us, because we start the development, and these requirements is kind of our baseline that guides us in the development. Okay, so regarding the high-level design, I don't think that it's a good idea to go pretty much drill down into the design. I will maybe talk just about two diagrams here. So the diagram of the flow, what can we see here is that we actually see here 3 components. It's kind of a standard description of the testing system. The first component is the Jenkins machine. The second component is a testing machine that includes actually the whole testing source code composed of robot framework and the Python plugin. Jenkins communicates with testing machine using SSH. And the third component is the machine or the cluster where the testing system is deployed, including Volta, Ponzi, MSDN controller, and the applications. And actually, the flow is composed of 2 subflows. The first subflow is deployment. So the testing machine system on top of the cluster using Helm and Kubernetes, and then it runs the test using the SSH, meaning CLI, or HTTP Web REST API. So this is kind of a very general diagram. And the second diagram that I want to talk to you here, that actually there are 3 layers of the system. So we will run Jenkins. From Jenkins, we will invoke robot framework project .robot file, and this robot framework, having Python plugin, will actually include inside, will import the Python implementation of different test stages. So that's pretty much all. What is very important actually for us to start development is to come into conclusion together with you guys what should be the entry point for our source code, and actually our suggestion is that we will contribute our code directly into the Volta repository. In Volta repository there is a test directory, and if I actually open the repository now, and if I come to Volta repository, we do have here test directory that includes right now 2 subdirectories, iTest and uTest. So what do we suggest? That we will add the third directory called A-tests, meaning automated tests, and this subdirectory will include all the code of our automated testing system. That means Python and robot files. I think that that's pretty much all what we wanted to talk about today. So yes, your feedback is very important for us. So please, we are in the very beginning. So I feel, telling the truth, we don't feel confident enough to understand what's going on, where to contribute the code, and how actually to start the actual work. So yes, please give your feedback. What do you think about things?
I have a question.
Yes.
Okay. What functions should the PONSIM have in this architecture?
What functions should it have? It should work as is. And if I open the list of the tests, yes, and this in the specific case, so we're gonna run these tests using, for example, the CLI command. So in order to, for example, to do provisioning, we run just PONSIM provisioning, and we check the results. So the idea here is not to change the code of PONSIM as the end controller of Volta. It's to test the system as it is using the CLI and REST API that we have. Does it answer your question?
Yes. I'm wondering if the PONSIM should emulate the data plane only, or control plane as well.
So as far as I understand, again, since we're gonna test the system as is, so we will require to run the actual traffic also. So that means that we will run the actual traffic through the RGs in order to see how it works. So yeah.
Okay, I understand.
Mm-hmm. Yeah. Okay, guys. Any other questions, feedback, whatever? Do you accept the location of our entry point in Volta repository?
Yeah, that's good.
Okay. Okay. So we actually start working, and we assume that this list of the requirements and the basic guidelines of the high-level design, they are accepted by the community, and that's how we gonna work. And then, anyways, any feedback, please provide anytime. Our next presentation gonna be once we are done with the POC, when we will have at least partially the first test running in Chords environment on top of Chords Jenkins. We will be happy to demo it to you. That's it from my side.
Oleg, just a quick question.
Mm-hmm.
How difficult? I mean, if somebody would have to take the work that you're doing and extend it to actually run the test on a real OLT,
mm-hmm.
What would be? I mean, is there something that you can keep in mind so that somebody later on can come along and extend your tests to have them execute on real hardware?
Yes, for sure. We will try to be as less tied to PONSIM as possible in order to be able in future run the same tests exactly on top of the real hardware with minimum change.
Okay, thanks.
Yeah, that's this is the intent, of course. And of course, from the point of view of the documentation, we will document everything here, even the information about how we're going to document it. We will enrich this wiki page with all possible informations. Of course, we will have the markdown documentation inside the repo, and we will align our code with the best practices of code contribution in order to make it, as easy as possible in future to be changed. Of course. Yes. Any other feedback or questions, guys? Okay.
That was really good.
Okay. Thank you very much. Big pleasure to start working with you.
Thank you, Oleg. Any last call for questions here for Oleg? Okay, I'll go ahead and take the presentation rights back for just a moment. And I believe, whoops, not presenting it. Hopefully you're seeing the just the recap of the agenda. I just went back to that screen. So for the discussion on the core changes, the current state, the changes that are planned for Beyond 2.0 as well, and then continued discussion related to Golang, then we will target that for Tuesday. So I'll ask everyone to please keep JIRA updated with current status, since we won't be able to get discussion time on the issues until next Thursday, since we're making this change to next week's usual topics. So please keep JIRA updated, and then also for the material that was just presented from NorthForge, keep in mind that the wiki is there, so please review that material as well and provide any feedback necessary. Last call for questions or comments before we drop for today. Okay, I think that's it. And then again, as usual, we'll ask the presentations to be made available to the Volta community as well. So thank you, everyone, and I will stop today's recording.